So for any prime p, we want to show that this number, minus 1, 2, 3, 4, 5, 6, 7, 8, 9, is divisible by p. And in this big number, all digits are repeated for p times. So I encourage you to stop this video and give this problem a think. But if you're stuck, I'll give you a hint. Use Fermat's little theorem. And as a reminder for what that theorem states is if p is prime, then for any integer a, we know that a to the p minus a is divisible by p. So you might kind of see that this theorem might be useful because here we are dealing with the difference of numbers, and here we have a difference of two numbers as well. Okay, so this is a hint, but I'll proceed with the actual solution. Firstly, let us introduce some notation because these numbers are rather lengthy. So let me call this number that has all digits running from 1 to 9 as a, and let me call this big number as b. So now I think it would be wise to look at this number more closely, and maybe rewrite it in a more convenient form. So the basic step that we can do is we can just rewrite this number as a decimal expansion, right? So we know that we'll have p1s multiplied by 10 to the 8p, because we'll have 8 types of digits left, and each of them is repeated for p times. Then we'll have 2's, also p of them, now repeated for only 7 p times. Sorry, so 10 times 7 to the power of 7p, and so on. And the last term is just gonna be p of 9's. Okay, so an immediate simplification that we can notice is that we can factor out p1s. So we can take this number outside of our bracket, and then inside we'll be left with 10 to the 8p plus 2 times 10 to the 7p plus plus 9. So why don't we repeat the same with a? So this was number b, and if we write a, this number, in the same decimal expansion, what do we get? We get 10 to the 8 plus 2 times 10 to the 7 plus so on plus 9. Okay? So what can you notice if you now remember my hint using Fermat's little theorem? Well, you can notice that here, if I subtract 10 to the power 8p minus 10 to the 8, I will be exactly in the setting of Fermat's little theorem. So I know that the difference of these two numbers will give me a multiple of p. And the same will be true for difference of this number, and so on. So if I now label this number as E, I will get that E minus A is equal to, well, write it down yourself. So it is a multiple of P. All right, so once we have this result fixed, we can now think about the result that we want. So what we want is B minus A. And so far, we have realized that E minus A is a multiple of P. So somehow we want to write E minus A here, but B is E times this number of ones, so we'll have P ones in front. Okay, so E times this will give us B, but then A times these ones will give us a different number, so we need to add it again. Not again, we just need to add it to cancel out, right? And then we have minus A. So the reason why I'm doing this is because this term is guaranteed to be divisible by P. Okay, we just need to figure out these guys now. So now, if we look at these guys, it will be A, P1s minus 1, which is A, 0. It doesn't really matter. So once again, A is the smallest of the two numbers. It's 1 to 3 up to 9. So how can we know anything about this number and its divisibility by P? Well, what we can notice is that 10 to the P minus 10 is again divisible by P due to Fermat's little theorem, is basically this number with P zeros minus 10, which is going to be 9 times 1, 1 P1s plus 1 minus 10. Right, so here I just rewrote 10 to the P in terms of numbers that we have already considered. And now I can just subtract 1 from 10 and take 9 outside and get this result. So now we're almost there, you see, because this number here is A times P1s minus 1, and this number is 9 times P1s minus 1. So now, another observation that we can make is that this number A is divisible by 9. The question here is, can you see why? You don't actually have to divide it using long division or something. There is a trick you can use to deduce divisibility by 9. So then, you can see that a times is also divisible by 9. Here, by FLT, we know that it will be a multiple of pi, so this is a multiple of pi, and then a divides 9. So actually this will be a factor of this multiple. So this guy will definitely be divisible by 9, and therefore it is divisible by p, which is really nice, because if we return to this expression here, we have a multiple of p here plus another multiple of p here. So we are done.